Hi everyone, I'm Isiki from FKE UTHM. So in this video, I'm going to show you the solutions for the final examination questions of semester 1, session 2025 and 2026. Okay, so this is the exam paper. So let's look at the first question. So the first question is from chapter 1. Okay, so for question Q1A, okay, show that a perfect conductor cannot contain an electrostatic field within it and briefly explain how this characteristic can be applied to build facility to protect electronic devices. So this question is about shielding, okay, how we use the conductor to perform shielding. Okay, so right, so this is the questions. Okay, so so what is conductor? Okay, so conductor, so you can write down that the conductor, okay, has abundant, okay, has many charges, has abundance, okay, of charges, okay, abundance of charges within it, and they are free to move. Okay, these charges are free to move within the material. Okay, okay, so you can draw a diagram. Okay, so let's say this is your conductor. Okay, so you can label conductor. Okay, so you have negative, positive charges. Okay, they are depolated randomly. Okay, just like this. Okay, so these charges, they're free to move. Okay, so you can say that this is a condition when no electric field is applied. Okay, is applied on this conductor, means that we don't put this conductor in a medium that has an electric field. Okay, so when you apply electric field or you put this conductor, okay, in a medium that has the electric field, for example, okay, so the electric field, for example, is coming this way. Okay, so this is the electric field. So what will happen to these charges is they will align to the directions of the electric field. Okay, so the electric field is this way. Okay, so negative charges, they will all accumulate here. Okay, and positive charges, they will accumulate at the other side. Okay, so as the result of these accumulations, okay, there is an internal electric field happen inside the conductor. Okay, inside the conductor. And this electric field, okay, I would say that this is internal. Internal. Okay, so this internal electric field is opposing the direction of the external electric field. Okay, so this is external electric field. External. Okay, as a result, this electric field cancel each other and makes the electric field there is no electric field inside the material. Okay, so there is no electric field inside the conductor. Okay, so this is a concept, so you can put it into the word by saying that when, okay, conductor, maybe I label first, conductor when exposed to electric field. Okay, so when an isolated, okay, you can say this is explanation of the things, okay, that I mentioned just now. Okay, so I read it in sentences. So when an isolated, okay, conductor is placed in an external, okay, electric field, okay, external, okay, the charges okay, are pushing, okay, are pushed along the same directions as the external electric field, okay. As a result, okay, electron or negative charge are gathered at one side, and positive charge are pushed to the opposite side. Okay, as shown in the figure. Okay, so the charge accumulated, okay, at the side of conductors, okay, create another internal electric field that oppose the directions of external electric field. Okay, so the electric field, so both electric field, okay, so both electric field cancel each other, and there is no electric field in the conductor. So this statement is telling you that why there is no electric field, okay, inside the conductor, okay, inside the conductor. So these conditions is made use, okay, in the applications of shielding, okay. Okay, shielding, and the purpose of the shielding to protect, okay, sensitive devices, electronic devices. Okay, so you can draw a diagram, okay. Okay, so this is the electronic devices. Okay, you can electronic devices, and then you draw the shielding box, okay, and with thickness, okay, so you can roughly shade it to show that this is another material, okay, conductor, okay, so cannot go in, okay, cannot go in, okay, EM wave cannot go in. Okay, right, so this is about questions 1A. Okay, I explain about how the conductor can be used to build facility to protect electronic devices. Okay, so this is the theory. Okay, so you should write like this. Alright, we look at the question B, question 1B. So consider two dielectric material with relative permittivity epsilon R. Okay, for K1 is 2.5. Okay, so this is K1. Okay, one dielectric material. And you have K2. Okay, K2. Okay, 1.7. K1 is 2.5. Okay, each fill half the space between the plate. Okay, so you can see the plate is in gray color. So this is the plate. Okay, gray color top plate and the bottom plate. Okay, so the material fills half of them. So half of it, okay, is filled with K1 and the other half is K2. Okay, so each plate has an area of this. Okay, so this is the area. Okay, each plate has area of A equals to this one, and the plate, they are separated, okay, by a distance of D. Okay, so calculate the capacitance of these systems. So the first step is you must identify what kind of capacitor is these structures. So you have parallel plate, right? So this is the parallel plate capacitor. Okay, parallel plate capacitor. Okay, so what is the equations of capacitance for these parallel plate capacitors? Okay, in general, it is epsilon A over D. Okay, A stands for the area, D stands for the distance. Okay, so since we have two material, it means that we have two capacitors. Right, two capacitors. So we have to decide whether it is parallel or series, right? Because we need to find the total capacitance, right? Okay, so we need to determine whether this arrangement is the parallel or series configurations. Okay, so if I redraw this capacitor again, okay, from the side view, this is the top and bottom plate, right? Top and bottom plate. Okay, assuming that the positive charge is accumulated at the top plate, okay, and the negative charge is accumulated at the bottom plate. Okay, so the electric field will go down this way. Okay, and half of it is K1 and the other half of it is K2. Okay, so this is K2 and this is K1. Okay, so this electric field, it has options. Okay, whether to propagate in K1 or propagate in K2. Okay, so when it has options, it means that this is the parallel configurations, because the electric field can choose whether to propagate in K1 or K2. So for the parallel capacitance, okay, so the total capacitance will be equal to C1 plus C2. Okay, C1 plus C2. Okay, very straightforward. Okay, so we look at C1. C1 is for K1. Okay, so K1. And C2 is for K2. K2. Okay, so C1. So C1 is equals to epsilon 1, A1, and D. Okay, so epsilon 1 is equals to, okay, epsilon R1 multiply epsilon naught. Okay, so this is, you must remember, okay, don't miss this epsilon naught. Okay, so epsilon R1 is 2.5, okay, and epsilon naught. So for the A1, A1 stands for the area occupied by K1. Okay, so K1 is occupying half of the area. Okay, so the area is 0.04. When we say half, it means 0.04 divide with 2. Okay, divide with 2. Okay, and the separation between the plate, okay, the separation you can refer is 0.01. Okay, 0.01. Okay, so you can start calculate these things. Okay, it's 2.5. Okay, so the answer is 4.43 times 10 power negative 11, or you can write it as 44.27 pico, okay, farad. Okay, so this is the C1. Okay, so we move on to C2. It's easy. C2 is equals to epsilon 2 A2 and D. Okay, so epsilon 2 is 1.7 epsilon naught, right? So this one still okay. I will straight away put it as 0.02 because it's half of it. Okay, so let's calculate this. 7. Okay, so the answer is 3.01. Okay, times 10 power negative 11 or 30.1. Okay, pico farad. Okay, so this is C1 and C2, and then to find the C total, you have to sum them up. Okay, that is 42.3. All right, I'm wrong, huh? Wait. This one should be 43, right? 43. 2. This one I approximate, so I'll put 3 here. 44.3. So 44.3 plus 30.1. Okay, picofarad. So is 74.4. Okay, picofarad. So this is the total capacitance, okay, for this configuration.